Hello, welcome to week 7 of Data 650. This week we are going to cover Eon and MapReduce, and a little later in the week we will also be looking at distributed database systems. Last week we studied the Hadoop distributed file system and its internal operations. We looked into detail how write and read operations are accomplished, and how a Hadoop system or a HDFS can be installed locally and configured, how we could design the cluster structure, estimate the number of data nodes, and we also looked at the user guide with commonly used commands for manipulating large volumes of data. But that is not the end, of course, it is the beginning. Once you store the data in HDFS, you want to be able to compute with it, and that brings us to MapReduce. So we also talked about the different versions of Hadoop and how resource management and computations became increasingly sophisticated with newer and newer versions being developed. Okay, so that was a brief refresher on last week's work. Now let's get into the details of MapReduce. Here is the title of the paper that was presented in 2004. MapReduce Simplified Data Processing on Large Clusters by Dean and Gemawat, both working at Google at the time. They came up with this paradigm based on older, more mature functional languages, including Lisp. So you should know the basic differences between a functional language, which is mostly declarative, and other languages that use a lot of statements. If you work with C or C++ or even Java, the older versions of Java, those are not exactly functional languages. The primary feature of a functional language is that all computations and all calculations are coded as mathematical functions. So you don't move data through your code, but instead you actually send the code to the data and you apply the code to the data. So the code itself is usually some function, and the data is passed into the input arguments and you get an output. Okay, so that's essentially what a functional language is. And the people at Google figured out that this was the best way to deal with computations on big data. And so this is a simple schematic of the programming model adopted by Google. So there is an input and an output, and each has a set of key value pairs. So you specify the map, which is a mathematical function. It takes in a key value pair and it emits a key value pair as an output. Okay, and we call this the intermediate value. So the map function essentially processes the input key value pair and it produces a set of intermediate key value pairs. And there is a reduce function which works on the output keys and combines all the intermediate values for a particular key and simplifies it and gives out usually a list of output values. Now, this simple programming paradigm, could accomplish a huge variety of tasks. You can think of simple word count, uh, or something more complex like a k-means clustering, and the power of this paradigm is that you could cast all those complex programs in terms of a map function and a reduce function, and internally or in the background, the power of this paradigm essentially comes from the fact that you have two simple functions which can be shipped out to the nodes that store the data and can be locally executed. Okay, and then the results can be combined together to get the final value that you are computing for. So that was the basic idea behind the original map. And here is how the execution was envisioned originally. You have input, which is a very large file store. Uh, it has been chunked up into blocks as we studied last week. And the map function acts locally on each block of data, and it produces intermediate results, which are key value pairs, which are then grouped together and run through the reduce programs to generate the final output. Okay, so that is the simple schematic behind how a MapReduce program works. Okay. All right. So now we are going to go into greater detail of exactly how Hadoop 3.0 accomplishes the MapReduce task. So it's not. There are many parts to it, and we will go through each of them in some detail. So on the left, you see a schematic that shows the input files in HDFS, and you see a lot of mapper nodes. These could be data nodes, or there could be more than one mapper node on a data node. Okay, it doesn't matter. But a mapper node is really the functional equivalent of a data node. Okay, but you could run multiple mappers on each data node. Okay, it's possible. So the data is present on the HDFS system on the different data nodes, and the mapper functions are shipped to those data nodes. The mapper functions act on the stored file, the stored data, and they emit key value pairs. Okay, so here you have shown about 4 different keys and corresponding values. Now, you can also create, or you can configure a partitioner and a combiner to run on the same mapper node. Okay, so this is how the partitioner and combiner help reduce computations and reduce latencies. Okay, so on the right hand side, I've shown schematically uh, the outputs of mapper functions. Okay, so here there are 4 mapper nodes, and I have listed 4 mapper functions. each mapper function has emitted key value pairs shown here. And remember that this is all happening in the memory buffer. Okay, the file itself is stored on the disk. It is read into the memory, and the mapper function is applied to this to the data in the file. Okay, and the mapper function emits the intermediate key value pairs. So where do those key value pairs go? They stay in the memory buffer. Okay, but you need the memory buffer for other things, like all the other daemons, the Hadoop daemons that are running on the cluster. So you only get to use about 80% of the memory buffer for the mapper operation. Okay, so remember that this schematically shows 80% of the memory buffer, but you have lots and lots of data on the disk, so this is going to grow in size. And what happens when the size of the emitted key value pairs exceeds the 80% of the memory buffer? Well, that's where the optional partitioner and combiner programs kick in. Okay, so the this is how the partitioner works. Okay, the basic function of the partitioner is to chunk up this data in a meaningful way. Okay, um, and what do we mean by that? So you take the keys and you compute some hash function. Okay, so the keys could be anything. They could be arbitrary strings or numerical values, or even maybe floating point numbers. But the hash function outputs are integers, and you divide the output of the hash function by the number of reducers you want for that job. Okay, so if you divide by, let's say, 500, then you are going to have 500 unique reminders. Okay, so for in this schematic I have assumed that there are only two reducers. Okay, so I'm going to divide each hash function output by 2. So I'm going to get a remainder of 0 or 1, and I will call them 1 and 2. So that's what you see here. Okay, so K3 results in a modular output of 2, K1 results in a modular output of 1, K4 results in a modular output of 2, and so on. Okay, and this function is very deterministic. So every time you apply K3, it's going to give you an output value of 2. Every time you apply K4, it's going to give an output value of 2. Okay, and what the partitioner does is, using the output of the hash function reminder, it groups the data into different subfiles. Okay, so how many subfiles are going to be there? Is going to be exactly equal to the number of reducers you have preset for your calculation. So if you have decided to have two reducers, there are going to be two partition files. Okay, and the combiner, again, if you can't figure a combiner, if you write in the code for a combiner in your MapReduce program, then what that is going to do is take each subfile for each key value, for each reduced or each partition value, and it's going to combine the values together. So you can see that happening here. K3 has a value of V3 that is preserved, and you got two rows of K4, and it combines the corresponding values together. Okay, that's all the combiner does. Okay, now all of this, the output of all these operations are spilled to the disk. Okay, so that is how you keep up with the overload of the memory buffer. Okay, and finally here we have the shuffle operation. Okay, this is a little bit tricky. Each reducer, I mean, once the mapper, partitioner, combiner are done, the reducers poll each mapper node and they do a pull operation. So for example, reducer 1 goes to mapper 1 and pulls this subfile, and it goes to mapper 2 and pulls the corresponding subfile, and so on. Okay, so now let's assume that there are 10,000, let's assume there are say 1,000 mappers and 500 reducers. So how many of these smaller files you will have across the whole cluster? That's going to be 500,000. And remember that all of these 500,000 files have to be shuffled, moved across the network. They have to go from node to node, from rack to rack, and maybe from switch to switch. Okay, so this is where uh, the most of the time is consumed in a MapReduce operation. Okay, all of these 500,000 tiny little files are being shuffled across the network. Okay, so it takes a lot of time to do that, and that's where if we can come up with methods to optimize that operation, optimize this shuffle operation, then you have certainly reduced the overall time of the MapReduce operation. Okay, MapReduce calculation. Okay, so once each reducer gets its file, it simply does a reduction operation. So it goes across all the keys and accumulates the values. Okay, we should also note that here before the shuffle there is also a sort. Okay, so here you can see that I have already sorted the partition files and the combined files by the key values. There is key 1 appears before key 2, here key 3 appears before key 4, and that goes a long way in reducing the time delays. Okay, so when the files are being shipped and the reduction operation is carried out. Okay, so those are the main um, operations that happen in a MapReduce task. Okay, and this is how you get this is how you do computations on big data. So for example, you could be doing a k-means clustering on a large volume of customer data, something that Amazon does all the time. So the keys could be items or customers or item customer pairs, and volume could be the amount of the number of purchases made. So this K3 can be, for example, the number of times a particular customer bought a certain type of furniture or a certain grocery item, and this could be the volume bought, purchased. Okay, and eventually what you want to do is figure out how customers and the items cluster together in this space. So all you have to do is class emit, the mapper has to just emit the customer unit ID in a multidimensional space, calculate the centroid values. Those will be the values emitted by the mapper function, and then you club them together, and what happens eventually in the reducer is that the centroid values are recalculated, recomputed, and then you repeat the process again and again, okay, till the centroid values converge. Okay, so that's a very simple example, and you have of course by now seen several examples of word count and related procedures. So all of those operations can be broken up into the subtasks, and you can calculate using this simple paradigm. Okay, so last week we looked at the evolution of the Hadoop system, or the Hadoop ecosystem. In version Hadoop 1.0, you had a simple HDFS and MapReduce on it. And then in Hadoop 2.0, you also had Yarn, which is the resource negotiator or resource manager upon which MapReduce system is has been implemented. So why do we go from version 1 to version 2? What are the advantages? How is version 2 better optimized? So those are the things we will be looking at in the rest of the lecture. Here is a very good schematic that shows you exactly what the difference is between MapReduce version 1 and the Yarn MapReduce version 2. Okay, so this is what happened in Hadoop 1.0. When a client launched a MapReduce task, there was a job tracker that was attached to the name node. There were task trackers attached to the data nodes, and the job tracker would take the MapReduce job, split it up into the map tasks and the reduce tasks, and it would schedule them on the data nodes. If a second client launched another MapReduce task, it would do the exact same thing all over again. Okay, let's assume we have a huge cluster. For example, we saw an example of the Google container system last time. You could have something like 10,000 data nodes in a container. And so imagine how many different MapReduce tasks will have to be run on that container. So every client has to go through the same job tracker to launch its task. Okay, so this becomes the biggest bottleneck. Okay, we are not criticizing the original implementation. You have to realize that it was a necessary step in the evolution of cluster computing. You had Hadoop 1.0, which was just a little bit of an improvement over the file system used for NUT, and the architects and designers of Hadoop 1.0 try to implement a computational system on top of HDFS, and that is what they came up with. And it was also supported by what was actually running Google at that time, which was the MapReduce algorithm that was published in 2004. Okay, so but that was the limitation of that algorithm. And here is Yarn and MapReduce 2, and you see already a dissociation between resource management and computations. Okay, so here the client talks to a resource manager, which is most of the time running on the name node, and every data node has a node manager. Okay, and the data node can be configured to run either an application manager or a container. Okay, so already here you see a level of flexibility that you don't have in MapReduce 1. So the client says, I want to run this MapReduce task. The resource manager looks around the entire cluster and picks a data node to be the application manager. Okay, that means, the application master. So the application master is going to monitor and initiate that particular MapReduce task. And the resource manager also goes around and finds enough data nodes to actually do the subtasks. Okay, so those are shown here as the containers. So the resource manager requests a certain fraction of the CPU and memory on each one of those node managers. Okay, and that is called the container, and those containers will serve as the subtask executors, which will all be under the control of this application manager. Now, if a second client comes in and launches a second MapReduce task, then the resource manager does the same thing. Okay, it goes around and finds a data node that can serve as the application master. It finds other data nodes that can work as the containers, and then those are ready to actually execute that MapReduce function. Okay, so that is the main difference between MapReduce version 1 and the Yarn helping MapReduce. Okay, so here is the job tracker in MapReduce version 1, and it was doing a whole bunch of tasks as we discussed before, and majority of these functions majority of the job trackers functions have been now relegated to the application manager. So there's the application master. There's going to be one application master for each MapReduce task, and some of the supervisory functions that the job tracker was doing are now managed by the resource manager. Okay, so you got the resource manager often running on the name node, and almost every data node is a node manager, and the node manager can be configured to be either an application master or a container. Okay, what is a container? It is a certain fraction of the memory and the CPU power on the data node. Okay, so you could have multiple containers and an application manager, a master on the same data node. So that's how flexible Yarn is. Okay, so let's start with a Yarn cluster. You have a resource manager and a whole bunch of node managers, and a client comes in and says, I want to run this complicated MapReduce task. Okay, so the resource manager looks around the cluster and finds a node manager to be the application master. So it sends, the application master sends a resource request. It says, in order to finish this MapReduce task, I need so many containers with so much memory and so much computational power. And the resource manager then sends the container IDs to the application master, and these are the containers. Now the application master takes over and runs the MapReduce task using those containers. If a second client comes in and it says, I want to run this other MapReduce task, the process is repeated again. The resource manager finds an application master which runs the second MapReduce task using other containers. Okay, and I already explained the concept of containers to you in the last lecture. So I want you to put all these concepts together and try to get a holistic picture of what is exactly going on in the cluster. Okay, there are two levels of operations happening on the same cluster at the same time. One is the distributed file system and its management, and the other is resource management for running computations, which are essentially broken down into MapReduce tasks. All right, so that is a very quick and brief overview of the Yarn and MapReduce, and it's gonna be very essential for you to know these details if you want to progress to the next step, which is the Spark cluster computing paradigm. Okay, and that's going to be described and studied in the following weeks. So please participate in the discussion, and on Tuesday, March 13th at 8 p.m. there will be a live lecture on distributed databases, particularly HBase, and you will have plenty of opportunity to ask questions about the overall Hadoop ecosystem as well as HBase. And I hope we will have a walkthrough of the HBase user interface to help you get started with the HBase assignment. Okay, thank you.